What's going on, everybody? Mr. Diamond back here, and now we're going to actually go over hybridization. I know in the last video we talked about how carbon hybridizes, but now we're going to actually work out example problems with hybridization. I'm going to explain it a little bit more detail. Now this table is going to be our cheat sheet. This is pretty much the easy method for identifying hybridization. All you really need to do is figure out what is the steric number, including lone pairs, and then that will tell you the hybridization. The way I personally like to remember it is I think of starting with S. S is number 1. Everything after that, the number 2 would be P. And then every number you go up for the steric number, you just need to be adding an exponent. Your exponents that's up here need to add up to your steric number. So in this case, there's an invisible 1 and an invisible 1. So SP is 2, and that is the steric number. SP2 would be invisible 1 and a 2. That would be 3. Invisible 1 and a 3 would be 4. This D here would have an invisible 1, so it would be S, so it would be 5, and then this one would add up to 6. Now, most of the time we're not going to deal with these, but I might throw one at you because you know me. I like to make you guys a little bit frustrated whenever I do stuff like that. But I'm telling you up front here, so do make sure you know this one. We're going to do this example here. Now, I've already sort of started working this out, mostly because I made a bit of an oopsie in my explanation in the previous version of this video, but I caught it pretty early, and I just figured, I could awkwardly sit there and try to explain it and go again because, there's no such thing as video editing, and then I was like, I'll just do it a second time. It's fine. It only took a few minutes. So we're going to actually go through it. If you want to pause this really quick and write it down here, I'm going to have it written on my paper as well, but if you would prefer looking at it this way, you are welcome to do so. Now we're going to go ahead and switch over to HandCam. Okay, ignore these awkward, very large black splotches that are definitely not my past failures. They are definitely not, I promise. So what we're going to do is we're going to look at this big molecule and try to figure out the hybridization of A, B, C, D, and E. Starting with A, and I've got my little cheat sheet up here. The first thing I want to point out is it doesn't ask us here, but what would happen if we were looking at hydrogen? Let's say, for example, we were caring about hydrogen. Well, hydrogen is only connected to one thing, so 1 would just be S. No P involved with that whatsoever. And the question I have, if that's the case, is, well, if it's just one thing, can it be a hybrid? And I assume you're able to figure out that the answer would be no. That doesn't sound much like a hybrid if it's just one thing. And you'd be right. Hydrogen never hybridizes. There's probably some real-world examples where that does happen, but we're not going to be dealing with any of that kind of level of crazy, weird chemistry. So you can just always assume hydrogen will never be hybridizing. Now for A, we're going to use our cheat sheet here. We've got 1, 2, 3, 4 things, and in that case, 4 things would be an sp3 hybridization. Now, if we think about this logically, and if I click back through my notes and go back to our geometry page that we were on earlier, pull that up. On our geometry page, trigonal pyramidal is basically the same shape as tetrahedral. It's only slightly different. It's pushed down just a little bit. I believe it's to 107.5, I think, if I remember correct. But this little bit that it's different is just because these electrons are trying to take up a lot more space. And the fact that it's taking up a lot more space is pushing it down, but it's not actually contributing. Like, there's nothing quote-unquote tangible here, nothing like an actual group attached to it. So we only count the geometry as this bottom part, but it's still got to make space for those electrons. It's still got to account for them. So that's why it's still attached to 4 things, and it still looks similar to our tetrahedral over here. So I switch back to my hand cam. That will kind of help explain why it's got to be sp3 hybridized. Now for B, that is right here, we have a carbon that's attached to 1, 2, and then 2 hydrogens would be 3, 4. 4 things is also sp3 hybridized. That's what we worked out earlier. Now for this one right here, I've already sketched it down here. And if we think of the normal energy level, the one we were using earlier, the same process is going to happen in this carbon that's labeled letter C, where this is going to hop up here to this energy level. But this time, because of the bonds it's making, because it's making 1 sigma bond and then 2 pi bonds that are going to be going around it. They have to go outside of that because we don't want to violate Pauli exclusion principle. We need to still have access to our p electrons. So what it's actually going to do, I'm going to scoot it up, and then I'm going to go down here so it's a little bit more obvious of where I'm talking about. We're going to go from here to the same middle point we had. But then, instead of like we had up here, instead of them moving up and moving down entirely and making one flat level, we still need 2 p orbitals. We still need 2 of these guys so we can go up and around and over the sides and connect to them. And so since we still need those, what is actually going to happen is going back to, I'm going to try to get this on as close to the same level as possible. Oh, this is like the same mistake I made last time. We're going to scoot this way over here. Nope, we're going to do the whole thing. We're going to do that. So we're going to have one S, then we're going to have SP, technically, again, this would be labeled 2, and then we're going to have 2P. And we'll have 1, 2, 3, 4, 5, 6. Now, I know that violates even more of the rules that you learned before, because now not only did we like pull one out of this level, but now we have half filled 2 levels. But based on what I've looked around, I had to double check myself because that's where I was kind of screwing up before. This is what it looks like it's going to happen. And this leaves you, down here we've got your SP. You've got this area that can form 2 hybridized bonds. So in this case, this would be this one sigma bond here. I'm going to make it a little more purple. This sigma bond between the carbon and the carbon. And that sigma bond between the carbon and the other carbon on the other side. That's going to be this hybridized chunk right here. I'll circle it in purple to make that clear. So it's getting 1 electron from the carbon on this side, 1 electron from the carbon that it's triple bonded to, and then these last 2 electrons are wrapping around, and these are the ones that are going on the outside edges of the carbon. Now, this is a way more complicated explanation than you're actually going to need for this. This is just showing you the way that, like, some professors, if they don't want to tell you the shortcut method, will make you do. You'll have to logic your way through, well, it needs 2 p orbitals to be able to form 2 pi bonds. The only way it could do that is if it hybridized only with 2 things, which means it must be an sp hybridized. We're not going to worry about any of that crap. You can just look and go, well, it's bonded to 2 things. It must be sp hybridized. It's still a good idea to understand this concept, but we're not going to have to do anything in there. And as you can tell by the fact that I was, so eloquently screwing it up last time of exactly where the electrons go in that process, most of the time, at least for the base level organic, you don't really have to worry about that stuff. At least my professor didn't make me. Okay, for our d orbital, or our d carbon right here, carbon is bonded to 1, 2, 3 things. 3 would be sp2. And we can use the same logic here. For this carbon, it would have to form a 1s with both electrons. Then it would have to form a 2sp2. And then that would leave just 1 lonely p orbital up here. But it needs that p orbital to form this double bond that's right there. It needs to have that. Otherwise, it can't do that. So these would be the sigma bonds that are formed here, here, and here. And then this would be that double bond that's forming on there. So the only one that's got left is E. E has a geometry of 1, 2, 3, so it's going to be sp2. Remember, I said it's only if it's bonded to a thing and only has a steric number of 1 do we get to say it's unhybridized. Hydrogen will never hybridize, but in this case it's still bonded to 2 other things, or it has 2 lone pairs. That counts to the steric number, so this would actually still have an sp2 hybridization, even though it's only attached to 1 actual thing, or it's only attached to 1 atom. Now, there is one major exception to this. Let me make sure I get back to it before I click back up to my screen. So the big exception here that you do want to know is that there is one time that we will care about in class where you can't just use steric number. In reality, there is a whole bunch of different exceptions to it, but this is the only one I personally think is worth the time. Lone pairs adjacent to pi bonds are more likely to form two sp2 instead of an sp3. So for example, this pair of electrons here, this would normally have been a steric number of 1, 2, 3, and then that would have been 4 because of the pair of electrons. So sp3 would have been for something that has a steric number of 4. Same thing here, same thing here, and same thing on this guy right here. All of those would technically, by our rules, have an sp3 hybridization, but all of these are more likely to be sp2. So I'm going to give you a moment to think about that and see if you can figure out why that is. It's another really complex kind of logical leap you've got to make, so don't feel bad if you don't. The reason for that is because of sterics and making electrons fit better in their cloud. Basically, if it's tilted downwards, it's going to be kind of pushing some of the groups closer to those clouds of electrons. What it's kind of going to boil down to is the orbitals will kind of overlap, and they will basically line up with one another. So instead of having those electrons pointed kind of angled this way and then therefore also angled down, you'll notice that in this region right here, they would kind of be bumping into each other. They'd be getting really close, and they don't want that because they're both electrons, and electrons are both negative. Even though we've got them kind of, coordinating here, we still don't want them to actually be overlapping. That would be bad, and that would be violating the Pauli exclusion principle. So instead, what's going to happen is it's actually going to go to sp2, and it's going to leave that p orbital intact. It's no longer going to be tilted or angled. It's going to stay kind of up and down, and that up and down is going to allow it to coordinate with all of the other p orbitals and form this nice, neat line where they're not going to mess around with each other, and they're not going to screw with each other, and it won't make our atoms or our molecules be looking really weird. So that's the one exception. If we go back to our picture here, it doesn't actually come up in this case. So we don't have to worry about it here, but you should definitely be on the lookout for it. That is definitely fair game for a test question, is for me to try to trip you up a little by putting one of those or two of those in the questions that I ask you. I hope that makes sense. If you guys have any questions, please let me know. This brings us to the end of this chapter. I know there's a whole lot of new stuff in it. Like I've kind of mentioned before in class, most of what we're dealing with is going to be a lot of front loading here. This is a lot of really advanced topics, but most of the rest of this we're going to be doing is just a lot of practice on some of the base topics that aren't nearly as advanced as this, so don't freak out too much. I hope you have an awesome rest of your day. I hope to see you, hear from you soon. This has been Mr. Diamond, signing off.